All right. So I will introduce myself real quick. My name is Daniel Smith. I am the President and Chief Engineer for Apertus Solutions, and I'm going to be presenting on the Fidelis platform that's been a work in progress for some time now. Some of you may have seen some of the capabilities I'm going to be presenting today as I've been advocating for them for across different communities. So we'll touch through this, and then at the end I can take some questions. I guess arrows don't work. I have to click. All right, so the agenda is I'm going to give an overview of the HAT security architecture. Once we walk through that, I'll give an introduction to the Fidelis platform, and then I'll have a few closing remarks. So HAT. So what is the Hardened Access Terminal? It is a security architecture that has been developed from past research and that I have evaluated along with architectures that I've had experience with to try to devise a forward-looking architecture that can be evolving as the threat landscape changes, as well as the hardware and software domains evolve as well. The formulation of the architecture was driven by a deep study into a lot of academic work in terms of trust, privacy, and safety, and how they all affected platform security. Existing and prior security architectures that I either had cursory involvement with or direct involvement with that were based around virtualization, and then a look at the cyclic evolution of virtualization hardware and software, how they've continually fed into each other and driven requirements for each other. So from an architectural standpoint, we defined 3 essential properties that the architecture must maintain: strong isolation, verifiable integrity, and fault tolerance. When you take these 3 properties, there are some derived properties that kind of fall out to achieve those. You have that the data flows within the system must adhere to the NEAT principle, the non-bypassable, always evoked, and tamper-proof. Your roots of trust need to provide explicit assertions. You cannot rely on blind trust or assumptive trusts. Components must be singular in their responsibility with minimal implementation complexity. That one is actually pretty deep. We want to isolate and have very tight cohesion inside of the components that we implement. Integrity statements that are made by the roots of trust must be very meaningful, backed by evidence to give you an idea of what the properties of that component has. And then a component's role and responsibilities and interactions with other components must be able to be represented on policy that can be evaluated for completeness and correctness. You need to be, when you apply this the policy, it needs to cover all aspects of how data can flow within the system. So if you want to, generally, this is a visualization of what a HAT platform would look like. You need to have a protection hypervisor at the base that is an L0 hypervisor. It, in turn, has a launch realm, a protected realm, and an end user realm. The launch realm is used to establish enough of the protected realm for the system to continue to come up. And the end realm is where the end users would load their system. And that exists outside of the security architecture of HAT. So just to dive into these components just a little bit with some definitions. So as you saw, we divide the system into 3 realms: a transient launch realm, the protected realm, and the end user realm, through the use of a protection hypervisor. So protection hypervisor basically is there to enforce roles and privileges separation on the platform and to mitigate communications across those the components within the platform. All data flows to and from an entity in the protected realm must be mediated by the protection hypervisor. The launch realm is a transient, so it only exists for a very short time. Its responsibility is for instantiating a minimal protected realm for the system to finish bootstrapping itself the rest of the way in a trusted manner. And as I said, since it's transient, it needs to be evicted upon completion before turning control over to the protected realm. The end user realm is under the control of the end user. It is for them to provide their own security architectures or implementation. The focus of the hat architecture is more about protecting the platform and itself, which is where you get into the protected realm, where you have the policy enforced isolation of all the resources of the platform. And you basically have inside that realm, you might think that that realm is meant to be a highly trusted realm, but no, it's highly trusted in the fact that it has strong assurances about what runs inside of it, so that you can actually have entities of different trustworthiness inside being delegated their degrees of trust. So why Xen? Why does Xen relate to all this? So the hat architecture, as I said, was envisioned to be agnostic of virtualization and hardware I/O isolation. So as long as you had a platform that provided those, you could use any hypervisor to achieve the hat architecture. The advantage to Xen and this architecture is that, or implementing this architecture, is that Xen already has the ability to do true disaggregation and function isolation. It already has a type enforced policy mechanism as a first-class citizen within it. Recently, the Argo showed up, and now we have hypervisor-mediated communications. And then, obviously, the two common ones a lot of have is it's open source, it has an active community, and it has a very mature security process. And finally, it's not tied to any one vendor or individual, so it's open to adopt these kinds of concepts that we're bringing. So in the end, Xen is the most flexible that is well suited to evolve to meet the needs of the hat security architecture. So putting a hat on Xen. So near-term efforts, everybody's aware over the last couple of days, we talked about the DomB capability. This allows us to increase the disaggregation and better separation of concerns inside the platform. So we can break components into smaller, cohesive components. Okay, thank you. You can leverage, so Trenchboot is coming along as well, so we can leverage it to bring DRTM awareness to Xen. And then on top of that, when that's integrated with DomB, it will actually wind up providing us a very strong chain of trust that's rooted in the hardware that gives us a really good launch integrity story for the platform. And then Xen provides the IO rec server capability that allows us to disaggregate security sensitive parts of the device model. So breaking up QEMU effectively is, if you want to think about it. Longer terms, disaggregating Xen into L0 core and an L1 capability hypervisor. Look at direct Flask enablement in Argo, so that way not only do we get mediated communications, but we get labeled mediated communications through the hypervisor. Using DRTM late launch to be able to relaunch the L0 core to reestablish load integrity at runtime about the core hypervisor, the L0 hypervisor. And then further down, we're looking at strong hardware isolation through PCI management and an emulation domain, which is actually very similar to some of the discussion yesterday on ARM and the safety island work. So that brings us to Fidelis. So Fidelis is the realization of all these theoretical concepts in terms of the architecture, the capabilities that we've been advocating to be brought into or bring to the surface in Xen, and then integrating them on the OpenXT platform. So using OpenXT as the base platform to build this. So if you're not familiar with OpenXT, it's an extensible platform with a focus on virtualization to bring a toolkit for hardware-assisted separation and tailorization for operating systems and users. It provides the base disaggregation platform, as it already has isolated network and management UI domains. And at a tool stack level, it actually has an API abstraction through dbus that can actually be leveraged to with Argo to disaggregate the platform services even further. So what winds up happening is we are making available a commercially supported derivative of OpenXT that we can evolve into meeting all the HAT security architecture requirements. So the features. So what do we have today? So we have Trenchboot integrated. We have, as part of the Trenchboot integration and leveraging the existing data at rest encryption that OpenXT has today, we expanded it to be more compliant with different standards. And we are actually actively standing up CVE monitoring to provide timely security releases of basically release 1. Upcoming, we have a true VTPM implementation for the 2.0 interface with proper authority provisioning coming, which I'll touch on all these a little bit later and in more detail later. We're going to increase the disaggregation of platform control. So we're going to get the hardware management and the platform control isolated. Right now, they're all inside of DOM 0. We're going to break that up. And we'll be integrating DomB with a DRTM-enabled Xen as those capabilities become available. All right, so the Trenchboot integration. So for those who are not familiar with Trenchboot, it is another project that I run. There'll be another talk later today or tomorrow on some of the work that's being done there, but it is focused on dynamic root of trust launch of the platforms using an x86 capability. We are looking down the road on how to bring this to ARM, but that is much further down the road. And it is basically, we will be taking the Trenchboot early launch capability and integrating it with OpenXT. As I said, as part of this integration, we've revamped how the data at rest works to meet our data at rest requirements. And then in doing that, what we've done is we've broken this boot sequence for OpenXT into 2 phases. We have our launch environment and we have our runtime environment. And each of these gives us a different place to make both encryption decisions as well as integrity assessments. So during the early launch, we can take SRTM and evaluate part of the early launch DRTM to do whole disk encryption for the environment. And then after we've achieved decryption of the whole disk, the runtime environment for OpenXT can be encrypted itself, which is traditionally how OpenXT works today. So for Trenchboot has the concept of a security engine that is used for the launch environment. The security engine that we've introduced with Fidelis provides key unseal for a local attestation. And we have an extended capability that we're providing underneath supported Fidelis, which gives you an attestation log verification capability. The local attestation key unseal capability and all we've done to do the Trenchboot launch of OpenXT. We'll be getting upstream to OpenXT in the coming months. And yeah, that's pretty much how we're handling the launch integrity with Trenchboot. Data at rest. So data at rest, for those who aren't aware, is focused on encrypting all your data when the system is in an unpowered state or in the process of coming up. As I kind of highlighted before, we split the boot phase into two, which provides us two locations for the data at rest decryption. The unlocking of each data at rest is directly tied to the platform integrity for that phase. So as I said, there's the early phase and then the runtime phase, the launch phase and the runtime phase. So the launch phase will verify the SRTM, give initial launch DRTM to control the whole disk encryption. And while the runtime phase kind of handles the final early launch DRTM control and decrypts any target runtime sensitive data. And then obviously later when we have late launch DRTM verification, we can actually use that to make decisions of whether or not to whether to lock or allow the DAR to remain unlocked or lock the data at rest. So some of the benefits include is the design is basically built around taking advantage of the availability of self-encrypted drives, but still will work with non-self-encrypting drives. For those that aren't familiar, pretty much every NVMe drive is a self-encrypting drive. The capability has kind of become standard there for NVMe. And then, of course, it naturally adapts to environments that have security requirements requiring 2 layers of data at rest encryption. Security support. So as I said, we're going to be delivering CVE updates for Fidelis, along with its OpenXT and Open Embedded components. So we will provide timely resiliency to our customers. So joining a lot of the security mailing lists, some of them have more requirements than others. So as we become available, we'll be joining the security disclosure mailing list for all the open source components. So that way we can provide more timely updates on our to Fidelis. There will be a Fidelis security bugs email address for customers to report, as well as third parties to be able to report disclosures. No bug bounties, sorry. And then obviously, as we are cutting security releases, we'll provide security notices to our customers so they understand what changes are coming in each security release. So looking forward now. So the first thing we're looking forward towards, hopefully by the end of the year, will be the VTPM capability. A VTPM is actually a security critical component for which we need to have high confidence on because we'll be relying on it. So therefore, it needs to be strongly isolated to ensure its security or its secrets are tamper resistant. This is one of the fundamentals about a TPM. If you look into the specs, it talks about protected locations and protected capabilities. So when you move a physical TPM into being virtualized, you need to maintain these because these are the core security properties of a TPM. Another one of them is to be able to properly provision in a provable manner, so that a way you can have trust, the root of trust for reporting. You know that the integrity reports coming out of the TPM are being signed by, or the signature can't be tampered with and spoofed in any manner. It must be tied to the root, the hardware root. So we need to be tied to the physical TPM. And it needs to be performant to scale with the number of workloads on the machine. You need to be able to provide a VTPM per any security critical component in the system. So we'll be reviving the Xen's existing VTPM architecture but we'll be replacing specifically the BPM domain with a new implementation that will still bind to the existing BPM manager while being able to appear as a proper MMIO device to any guest that it's attached to. So this is using the Xen's IO rec capability. And so then we will be able to spin up multiple instances of VTPMs that can be properly provisioned and provide integrity to every VM that needs a strong VTPM implementation. The next thing on the roadmap will be the increased disaggregation. As I said, we're going to split the platform control and the hardware management that's currently co-located in DOM0 and break those apart into isolated VMs with policy controlling communication between those domains. So most of that will be achieved just using existing Xen capabilities, such as the hardware domain to be able to isolate the physical hardware and manage the device pass-through. And we'll also be bringing physical storage isolation to keep tighter controls over the storage within the platform. DomB DRTM. So one of the things about DomB is it will provide Xen with a unique hypervisor capability that Fidelis will tailor to increase platform launch integrity. So when we begin bringing DomB in along with the DRTM, it will be the next major step in us aligning to the HAT architecture, because it'll actually truly allow us to implement the launch realm as an isolated realm within the launch of the platform. It will allow us to deprivilege the disaggregation boot process. So in the previous slide, when I talked about disaggregating DOM0, that will still happen in a traditional DOM0 launch system. Once we have DomB, we'll now no longer need to rely on DOM0, and we'll be able to just have policy labeled domains that for control and for hardware. And then when we bring the DRTM capability into Xen, that will allow DomB to work in conjunction with Xen as part of a DRTM launch for the platform. Capabilities and planning. So this is even looking a little bit further ahead. So the PCI isolation. So the protection hypervisor, using the HAT architecture terms, needs to be able to split the PCI bus between itself and a dedicated entity, a PCI manager that is outside of the protection hypervisor. Basically, the protection hypervisor needs to be able to mediate all access to the bus, but it only needs to do so to the degree to ensure that the PCI manager cannot compromise the protection hypervisor. So there was a lot of discussion yesterday in the PCI discussion yesterday about how much logic Xen needs to have. So from our perspective, the way we're approaching it is that the protection hypervisor, in this case Xen, needs to have enough logic to be able to know what's on the bus and to ensure that nothing commands a PCI device or the IOMMU to give it access to the memory regions within the protection hypervisor. The PCI manager itself, we are advocating to be a single purpose built kernel. So a runtime kernel, well, I wouldn't call it a runtime kernel, a microkernel, so that we can reduce the attack surface, and it should only have the logic for managing the PCI devices and the IOMMU, and then emulating those devices and the buses up to any of the nested hypervisors. And that should be it. I kind of blew through the slides pretty quick. In the end, if you want to do any offline discussions over it, You can reach us. We have our website's a little delayed. We have a new website rolling out soon that'll have a Fidelis product page landing. But in the meantime, you can always reach out to us. All right, at that, any questions?
Do you see? So can you remind me what your this is a product you guys are going to sell with this in it? And do you see a lot of other interest in other use cases as far as using it as a downstream?
So right now there's a certain customer set that's targeted with it. As far as additional uses, we're always open for discussion. Does that answer your question? I'm not trying to be obtuse, but
No, I was just curious if you expected other downstreams already, or if that was just kind of, where it's open source, and so you can use it if you want.
So yes, a lot of the open source componentry that we will produce will be upstreaming into OpenXT. So you can kind of view OpenXT as the open source version of Fidelis, provided unless there are some components that the community decides they're not interested in, then we might maintain those independently. And then any components that are not open source that feature add capabilities, they would come with the purchase of the product, or with support of the product. Actually, you don't buy the product, you buy support. But
okay, yeah, that makes sense.
So somebody was asking if they could get the slides. George, are you guys going to post the slides on the page?
I think we can post it. Actually, I think you should. Oh, actually, Daniel.
Yes.
If you go to upload slides again, yes, there should be a little checkbox that you can say allow download slides.
Okay.
And then once that's checked, then people can download these slides. It's a bit obtuse, so if you can't figure it out, like I can take presenter and try and get it working.
Actually, I can. So the current upload is still there, and I unchecked I allowed the download. So let me see if can you download them now? If not, I'll re-upload them again.
Oh yeah. So in the lower left, it's hard to see, but in the lower left-hand corner, there's a little download icon where we can now download the original presentation.
Yeah.
And as Deb says there, you can email them to xenevents@linuxfoundation.org, and they'll put it in on schedule.
Okay, I'll do that as well.
So, okay, cool.
Excellent. Andy, do you have any questions? Besides that icon.
I mean, you really were missing a trick there.
You know what? I was putting this together on Sunday, scrambling to get them finished on Sunday, with the expectation that I possibly could have presented on Monday. And then at this point, I was done. So, but any technical questions from you?
Not really. I mean, as people who are listening to this may not know, we have actually discussed this quite a bit over the past year or so. So I think at least I'm fairly up to speed on the technical aspects. You do have another question in the chat, though.
Yep, I see that. No. So the VTPM, so the existing VTPM implementation in Xen, basically the way it's rooted in the hardware TPM is the fact that there is a amount of storage that is related to a VTPM. Typically, it's so in the case of a TPM 2.0 is the seeds for the different authorities, the hierarchy seeds. as well as NVRAM, and the EK cert. So these need to be sealed and protected. And so what the existing architecture does is that the TPM manager controls the encryption of the VTPM storage. So in terms of performance, there's the decryption of it as the startup of the VTPM, but at that point, all processing is done inside of the VTPM. There is no more reach back to the physical TPM unless you do something a much more advanced concept called deep attestation, where you want to attest the entirety of the platform and not just what the VTPM is holding. Does that answer your question, Sergey? So all right, so let's be clear. The existing VTPM inside of Xen, I'm answering Igord's question. So the existing VTPM implementation inside of Xen is a TPM1.2 like para-virtualized TPM. That's the interface that you get on the client side. On the back end, the TPM manager can actually talk to a 2.0. What we will be doing is we will actually be making, and yes, I will be upstreaming it to Xen. I'll work with the community on how they want that to land and where they want it to land. But it will be similar to the existing VTPM, where it is built off of the existing Minios microkernel, and it will incorporate the reference implementation for the TPM2. So yes, it will appear as a TPM 2.0 device to the client. Let's see here. Do you plan to stick a VTPM stub domain with Burroughs TPM? No, so neither. For Jason, the TPM implementation will actually be the reference implementation published by Microsoft that they actually keep up to date as they make adjustments. So, live migration of hardware that has a VTPM in it, that has been done before. It is very hard. So the focus of OpenXT and thereby Fidelis is more on in client devices, more than server environments where you would be looking at live migration. Down the road, we might consider looking at server platform virtualization. You can do it. There's nothing stopping you, but except for when you get into things like dealing with the tricky situations like live migration for VTPM backed devices that are bound to a physical TPM. The way it was done, if I recall correctly, is due to the fact that since the physical TPM or the VTPM manager handles the encryption of the VTPM storage, in theory, that could be securely transferred to the VTPM manager on the other side to allow migration. So, but not within the scope in any immediate future for us. All right, any other questions? Yep. No problem. Thank you guys for the good questions. All right. Unless there are any more questions, I'm around for the next 2 days, so we can obviously you can ping me. We could jump into a room for a discussion or in the hallway chats. Just let me know. All right. Thank you.